So today we're going to talk about section 4.3, which is exponential decay. We have already talked about exponential growth, so you will see a lot of similarities in the discussion and in the formula. There's just one slight difference, and I'll point that out now. If you look at this formula, A equals P parenthesis 1 minus R parenthesis to the n, when we had exponential growth, that was a plus. And now as we work with exponential decay, that will be a minus. That's the only difference, is the plus turns to a minus. So first I'm going to do a little definition of exponential decay. This is when the quantity decreases by the same amount, or not the same amount, sorry, the same percent from one time period to the next. And then all of these definitions, like A is your ending amount, P is your initial amount, R is the rate as a decimal, and N is the amount of time. All of that is the same as when we did it with exponential growth. So I have an example. Example 1 says a young salmon passes through a turbine on a hydroelectric dam on their way to the ocean, and every time they pass through a turbine, about 15% are killed. Of the 100,000 young salmon, how many of those survive after passing through 6 turbines? So we're going to use this formula. A is our ending amount, that's what we want. P is the initial amount, which is 100,000. 1 minus the rate here is 15%, and as a decimal, that's 0.15. And the amount of time in this one is 6 for the 6 turbines. If we type all of that in our calculator, we end up with 37,715 remaining salmon. For the next example, example 2, this one, it deals with half-life. And the only difference between the first equation that we used in this one is in the parentheses, it's already going to be a half always. And then the exponent is a little more complicated. So this says the half-life of aspirin is the amount of time it takes for 50% of the drug to be removed from a person's body. So you take an aspirin, and then time goes by, and it goes from being in your body to half of it being in your body, and then half again, and it just keeps decreasing. So it says, suppose you take 500 milligrams of aspirin. It has a half-life of 3 hours. How much aspirin will be in your bloodstream after 24 hours? So we're going to take and use this formula. It's A equals P, which is the initial amount, which is 500. Half, if you like half, use half. If you rather use 0.5, you can use 0.5. And then here, little t divided by big T. Little t is the amount of time, which in this case is 24, divided by capital T is the half-life, 3. Basically what you're doing is figuring out how many time periods have passed in 24 hours, or how many half-life time periods have passed in 24 hours. If a half-life is 3 hours, there's 8 half-life time periods that have passed. So what we'll do then is take that, plug it in our calculator, and we end up with 1.95 milligrams left after 24 hours. All right, we'll keep going and do this last example. Example 3. It is finding an exponential decay rate. So with this one, it doesn't tell you the rate right away. It gives you other information. So this one says your basal metabolic rate, your BMR, is the number of calories you expend in a day while in a state of rest. So this is just going about your daily routine. How many calories do you burn? Not working out, playing a sport, just kind of going through your routine. Informally, it's the number of calories that your body uses to stay alive each day. So studies show that the BMR decreases in adulthood. Here it says a man's BMR is 1,800 calories when he's 20, and then it decreased to 1,710 when he was 30. So what we're going to do is try to find his BMR when he's 40 using the same decrease percentage. So the first thing we'll do is find the rate. And up here, if you look, a sub 1 over a sub 0, that just means take the bigger amount divided by the smaller amount. Or in this case, sorry, a sub 1 is going to be later in time. So later in time is the 30-year-old amount, so that'll be 1710 divided by the newer amount, which is the 20-year-old one, and that would be 1800. So if we divide those, we end up with 0.95. And then if we subtract that 1 over, we end up dividing both sides by negative. We get r equals 0.05. So the rate is 5% that it decreases every decade. So then we're going to go and use that formula from the front. A equals P, which is our initial, 1800, parenthesis 1 minus the rate, which was 0.05, and every decade, and we're looking for age 40, which would be 2 decades. And if you type all that in, it is 1,624.5.